In the world of mathematics, we often encounter situations where we need to express relationships that are not about exact equality. This is where the concept of inequalities comes into play. Instead of using the equal sign, we use special symbols to show that one quantity is greater than, less than, or not equal to another. Think of it like comparing the heights of two friends. They might not be the same height, but we can still describe their relationship using terms like taller or shorter. Inequalities help us express such comparisons mathematically. Instead of just saying two things are different, inequalities allow us to be more specific about how they are different. This makes them incredibly useful tools for describing a wide range of real-world situations. Just like any language, inequalities have their own set of symbols that we need to understand. These symbols are the key to unlocking the meaning behind these mathematical statements. Let's take a look at the four main inequality symbols. Greater than. This symbol indicates that the value on the left side is larger than the value on the right side. For example, 5 is greater than 3. Less than. This symbol implies that the value on the left side is smaller than the value on the right side. For instance, 2 is less than 7. Greater than or equal to. This symbol combines the greater than symbol with the equal sign. It means that the value on the left side is either larger than or equal to the value on the right side. For example, x is greater than or equal to 4. Less than or equal to. This symbol combines the less than symbol with the equal sign. It implies that the value on the left side is either smaller than or equal to the value on the right side. For instance, y is less than or equal to 10. These symbols are the building blocks of inequalities, allowing us to express a wide range of mathematical relationships with precision and clarity. Inequalities are not confined to textbooks and classrooms. They have practical applications in our everyday lives. Let's consider a few examples to see how inequalities manifest in real-world situations. Speed limits. When driving on a highway, you'll often encounter speed limit signs. These signs use the less than or equal to symbol to indicate the maximum speed allowed. For instance, a speed limit sign that reads speed limit 65 miles per hour can be represented mathematically as speed less than or equal to 65 miles per hour. Budgeting. Imagine you have a monthly budget of $500 for groceries. To stay within your budget, your total grocery expenses should be less than or equal to $500. This can be expressed mathematically as grocery expenses less than or equal to $500. Minimum age requirements. Many amusement parks have minimum height requirements for certain rides to ensure safety. For example, a roller coaster might have a minimum height requirement of 48 inches. This can be represented mathematically as height greater than or equal to 48 inches. These examples highlight how inequalities are woven into the fabric of our daily lives, helping us make sense of limitations, comparisons, and ranges of possibilities. Section 4. Linear inequalities. Solving the puzzle. Linear inequalities, like their equation counterparts, involve variables raised to the first power. Solving linear inequalities is similar to solving linear equations, but there's a crucial difference. The solution is not a single value, but a range of values that satisfy the inequality. Think of it like finding all the possible combinations of coins that add up to at least $1. You could have a single dollar bill, 4 quarters, 10 dimes, or countless other combinations. Similarly, solving a linear inequality involves finding all the values of the variable that make the inequality true. The goal is to isolate the variable on one side of the inequality symbol, just like we do with equations. However, we need to be mindful of a special rule when dealing with multiplication or division by negative numbers. Section 5. A golden rule. Flipping the sign with negative multiplication and division. When multiplying or dividing both sides of an inequality by a negative number, the direction of the inequality symbol must be reversed. This rule is crucial to maintain the accuracy of the inequality. Imagine multiplying both sides of the inequality. 2 is less than 5 by negative 1. If we don't flip the inequality sign, we get negative 2 is less than negative 5, which is incorrect. To maintain the truth of the inequality, we must reverse the sign, resulting in negative 2 is greater than negative 5. This rule ensures that the solution set of the inequality remains valid, even after performing operations with negative numbers. It's a fundamental principle that governs the manipulation of inequalities. Section 6, Step-by-Step Guide, Solving a Linear Inequality. Let's illustrate the process of solving a linear inequality with a simple example. Solve for 2 plus 5 is less than 13. Step 1, isolate the term. Subtract 5 from both sides of the inequality. 2 plus 5 minus 5 is less than 13 minus 5. 2 is less than 8. Step 2, isolate. Divide both sides of the inequality by 2. 2 over 2 is less than 8 over 2, is less than 4. Solution. The solution to the inequality is less than 4. This means that any value of that is less than 4 will make the inequality true. It's important to note that if we had multiplied or divided by a negative number in any of these steps, we would have flipped the inequality sign accordingly.